Okay, so to fold up this graphic organizer, we're going to start by folding it in half along the dashed line. And then with your scissors, you can go ahead and cut along that fold. Okay, so we have 2 half sheets of paper. And one of these half sheets has a dark line through the center. Okay, that one we're going to fold in half the long way and just give it a little squeeze. There, we don't have to fold the whole way across. And then with your scissors, you're just going to cut right along that solid line and then stop. So don't cut the whole way through the paper, just through that solid line, so that when you open it up, there's sort of a little pocket there, like a slit through the center. Okay, then on the other piece, there are solid lines along the top and the bottom edge here toward the middle. We're going to just cut right where those solid lines are located, like that. Okay, now this part can be a little bit tricky. You want to make sure that you put the pages in the right way. So we're going to find the one that says example 2 and lay that flat on the desk. Then we're going to take this other part here that has example 1, and we want example 1 to come before example 2. So we're going to fold this in half and just kind of squeeze it there like that, and then insert that into the slit that we cut. And then when you lay it out flat, okay, then we'll have the pages of the book in order. So find the cover page and then give that a crease. And since we inserted the one inside the other, the pages should all stay together without needing staples or tape or anything. So we'll have example 1 followed by a checkpoint problem, example 2 and another checkpoint, example 3, and then our last checkpoint. And on the back of the notes is a table with all of our transformations for the trig functions listed there, and some always, sometimes, never problems at the bottom. Okay, so this is on the back of the foldable notes booklet. This is our table of transformations for trig functions. And the equation here at the top, A, is times the function, either sine, cosine, secant, cosecant, tangent, or cotangent. B, then times the quantity x minus h, and plus k. So these should look familiar from when we did transformations of functions earlier in the year before trigonometry. The k was the vertical translation, which would move the graph up and down. For trig functions, we call that vertical displacement instead of a vertical translation, but it's the same process, same outcome, just a different vocabulary word. The h we would call, with regular functions, a horizontal translation. In trig functions, we refer to the shift left and right as a phase shift. Okay, the a value tells us if there's been a reflection or a vertical stretch or shrink. And if it's a sine or cosine graph that has absolute extrema, that amplitude, the vertical stretch and shrink, would change depending on that A value. So to find amplitude, we would use the absolute value of A. The A, when it's negative, would be a reflection in the x-axis. And the A value is going to change the range for many of these parent graphs. Only the tangent and cotangent range would not be affected by a vertical stretch or shrink, because tangent and cotangent have a range of all real numbers. But it will affect the guide points on the tangent and cotangent functions graph. Okay, then the B is the horizontal stretch and shrink, and that affects the period of the graph. And the period, remember, is the length of one cycle of the pattern before it repeats on the coordinate plane. If your B is negative, then you also would have a reflection over the y-axis. So go ahead and pause the video. Try these questions A, B, C, and D on your own. You're going to answer always, sometimes, or never true. And then when you're ready to go over them, you can resume the video. Okay, so when B is greater than 1, the period decreases. So if we look down here at the horizontal stretch and shrink, to find the period, we take 2 pi and divide by b for the sine and cosine. Same for secant and cosecant, 2 pi divided by b, that's the period of the function, divided by the b value. Tangent and cotangent have a period of pi instead of 2 pi, so to find the period when there's a b value, we take pi divided by the absolute value of b. So if b is greater than 1, that means we're dividing by a bigger denominator than 1. That's going to make this value smaller, which will make the period decrease. So that would be always true. A phase shift changes the domain. Phase shift, remember, is a translation to the left or the right. So it would not change the domain for sine and cosine because their domain is all real numbers. But secant, cosecant, tangent, and cotangent, they have vertical asymptotes that would be affected by a phase shift. So the domain sometimes changes depending on whether you have sine, cosine, cosecant, secant, tangent, or cotangent. An amplitude change affects the extrema. So if you're looking at sine and cosine, a change in amplitude is definitely going to change your extrema because the amplitude is half the distance between your absolute extrema for sine and cosine. And then D, a phase shift changes the range. So if you have H value that's shifting your graph to the left or the right, the range would not be affected for any of these functions because the range is the y values, and a horizontal shift left or right only changes x values. So D is never true. Okay, let's take a look at example 1. We were asked to identify the features and sketch the graph of 3 cosine of the quantity x plus pi over 2 minus 1. So to do these transformations, we're going to start by taking a look at the parent graph of the cosine function so we can find some anchor points to work with. So if this is my max of 1, my min of -1, and then we'll have 4 tick marks for our quadrantal angles. So this one would be pi over 2, then half the circle is pi, 3 pi over 2, and the whole circle is 2 pi. So for the parent graph of cosine, if you recall, we start at a y-intercept of 1, that's the maximum, then pi over 2 is a 0, pi is the absolute minimum, 3 pi over 2 is a 0, and 2 pi, we're back at the max, that's coterminal, is 0. So one cycle of the parent graph of cosine from 0 to 2 pi looks like this. So we can use those 5 anchor points as the points that we're going to transform in our table. So we're going to start with our y-intercept of 0, 1. Then our first 0 is pi over 2, 0. Then we have that absolute minimum at pi -1. 3 pi over 2 is a 0. And then 2 pi is an absolute max of 1. Okay, then looking up at our equation, the A here is 3. And the A, since it's positive, tells me there's been no reflection, but there has been a vertical stretch of 3 units. So to do that vertical stretch, we're going to multiply each of these y values by a equals 3. So the x stays the same, and then 1 times 3 is 3. The x pi over 2 stays the same. 0 times 3 is 0. My x of pi stays the same, and negative 1 times 3 is negative 3. Then my x, 3 pi over 2, stays the same. 0 times 3 is 0. And 2 pi, that's the x, that stays the same. And 1 times 3 is 3. Okay, that was our vertical stretch. Now the b value is the coefficient on the x. Since the b is a 1, then dividing all of these x coordinates by 1 doesn't actually change its value. So we can just skip right over that column, or you can draw arrows across, and we'll move on to the h. The h is the opposite sign of what we see in these parentheses, because remember the transformation form is x minus h. Since we have x plus pi over 2, the h is a negative pi over 2, which is going to shift this graph to the left since it's a negative. So we're going to add negative pi over 2 to each of our x values. So 0 plus negative pi over 2 is negative pi over 2, and the y stays the same. Then we have pi over 2 plus negative pi over 2 is 0, and the y stays the same. Pi plus negative pi over 2 is pi over 2, and our y stays the same. 3 pi over 2 plus negative pi over 2 is pi, and the y stays the same. And then 2 pi minus pi over 2 is 3 pi over 2, and the y stays the same. Okay, then last is the k. K keeps the same sign, so our k is negative 1, and that's the vertical displacement, or vertical translation of our graph. So we're going to add k equals negative 1 to each of these y values to do the vertical displacement. So the x stays the same, and then 3 plus negative 1 is 2. The x stays the same, and 0 plus negative 1 is negative 1. The x stays the same, pi over 2, and negative 3 plus negative 1 is negative 4. The pi is the x, that stays the same. 0 plus negative 1 is negative 1. And then 3 pi over 2 stays the same, and 3 plus negative 1 is 2. So now we can go ahead and plot those points on our coordinate plane. So at negative pi over 2, I'm going to go to positive 2 in the y direction and plot a point. Then 0, negative 1 is the new y-intercept. Pi over 2, comma, negative 4. Then we have pi, negative 1. 3 pi over 2, comma, 2. And that would be 1 cycle of my transformed cosine graph. Now we want to graph this over the interval negative 3 pi to 3 pi. So I need to repeat this pattern now going in the left and right directions. So if you notice, it starts in the same pattern as the cosine parent graph, up, middle, down, middle, up. So we're going to go ahead and continue that pattern starting up. That makes this next one at 2 pi middle. Then we're going to, oh, whoops, too high. There we go, middle. Then we're going to go down to the minimum, then back to the middle, and then back to the maximum. And so this would be another cycle. Then we can do that in reverse. So we'll go back to the middle, then our minimum, then to the middle, then to the maximum, then back to the middle, and then back to the minimum. And we can put a continuous wave through those guide points. Oh, I missed one. And that would be our parent graph, or not parent graph, sorry, rather our transformed graph for 3 cosine of the quantity x plus pi over 2 minus 1. So the absolute minimum now of our graph is at -4. And that minimum is occurring, the first non-negative minimum is at x equals pi over 2, but then we need plus or minus k times and then the distance to the next. So if each of these tick marks is pi over 2, we're going 1, 2, 3, 4 tick marks. That's 4 pi over 2 or 2 pi. So x equals pi over 2 plus or minus k times 2 pi. The absolute maximum is up here at positive 2, and our first non-negative maximum is located at 3 pi over 2 plus or minus k times, and then the distance between maximum, it's another 4 tick marks, so that's 2 pi. And those are true for k that is an element of the integers. Right? K can't be any real number because fractions and decimals wouldn't give us complete revolutions around the circle of 2 pi. Okay, then let's go ahead and write out our transformations. So our vertical displacement, that was the k, and our k value was a -1. So this went down 1 unit. The amplitude, that's half the distance between the absolute max and the absolute min. So if I look for my vertical displacement, I've got 2 as my max and -4 as my min, and that's going to be 2 minus -4 divided by 2 to find half the distance between them. And 6 divided by 2 is 3. So we have an amplitude of 3 units. Okay, the phase shift is the h value, and we phase shifted -pi over 2 units. That's a shift to the left, pi over 2. Okay, to find the period, we take 2 pi divided by the b, and our b here is 1. So 2 pi divided by 1 is 2 pi for the period. Then the domain of any sine or cosine graph is always the set of all real numbers, -infinity to +infinity. And the range is going to be bound between the extrema. So we need brackets around this interval -4 to 2 because it is inclusive. Okay, then let's use a calculator to go ahead and check this graph and see how we did. So in your calculator, you want to go to the mode and make sure that you're in radian mode, since our graph here is got a scale in radians. And then we're going to go to the window button, and we're going to change our grid to match the grid that's on our coordinate plane. So let's go from -3 pi to +3 pi. And our scale, we're going in increments of pi over 2. Then our y minimum is -5, y maximum is a 4, above that 3, and the scale there is going by 1s. Now we'll go to the y equals and put in our function 3 cosine of the quantity x plus pi over 2, and then minus 1. And then we'll click on graph, and here comes our sketch of the graph. And if we hit trace, we can type in an x and see if we get the y that goes with it. So if I type in negative pi over 2 and press enter, there's my y value of 2, which matches my table. If I put in a positive pi over 2, whoops, press enter, there I get back negative 4, which matches the point that I had put in. So I can see that my graph that I sketched matches the graph in the calculator. Okay, so now you're going to pause the video and try this checkpoint problem in the next page of your notes. And when you're ready to go over it, go ahead and resume the video. Okay, so the anchor points on the sine parent graph are 0, 0, pi over 2, 1, pi, comma 0, 3 pi over 2, negative 1, 2 pi, comma 0. Then we're going to multiply each of those values by a. The y values in our a is negative 2. So when we multiply each y by a equals negative 2, we're going to get these points. Okay, then our next value is the b, and the coefficient on x is a 1. So we divide each of these coordinate x coordinates by 1, which gets us the same thing again. Then next comes the phase shift, which is the h, and h is positive pi over 2. So we're going to the right pi over 2 units. That changes each of the x coordinates, increasing them by pi over 2. Then our vertical displacement is the k, and our k is positive 3. So we're going to add 3 to each of these y coordinates to get this set of ordered pairs. Then we sketch those points on the graph and continue the pattern, and then trace through with a smooth continuous wave. And we end up with an absolute min here at positive 1. And the first non-negative minimum is at pi, and then plus or minus k times 2 pi to get to the next one. You can write that as 2k pi or k2 pi, 2 pi times k, however you want. Absolute maximum here is 5, and that's occurring at 0. We don't have to write the 0, so that's just plus or minus k times pi times 2, so plus or minus 2k pi. The vertical displacement is the k, and we're adding 3, so that goes up 3. The phase shift is the h, and since it's positive, we're headed pi over 2 units to the right. The amplitude is half the distance between the absolute extrema. So if we take 5 minus 1, that's 4, divide that in half, and the amplitude is 2. The period is the 2 pi divided by b, and our b is 1, so the period is 2 pi. The domain for any sine function is all real numbers, and the range is bound between the absolute extrema. So we have the closed interval 1 to 5, and you need brackets because the 1 and the 5 are inclusive. Okay, then if you used your calculator to check, right, this would be your function in radian mode with these window dimensions, and you'll end up with this graph.